All right, welcome everyone back to 161. This is our third lecture. And today we will be talking about one of the main components of our course, which is the subject of problem solving by search. And just before we get started, let me just say a couple of words on logistics. I did set up a Zoom link for my office hours, which are on Wednesday at 3. You can find this on CCLE next to the other Zoom links. And regarding the wait list, I did ask the department to actually admit the wait list. So hopefully this should happen any minute now. Now, today's lecture is going to be all on the whiteboard. So I will be turning my camera off next, and then we will head to the whiteboard so that we can start with our discussion. All right. So as discussed in the introduction to the course, we have a number of major subjects. One of them is going to be, which we'll start with today, is problem solving using search. We will spend actually about 5 lectures on this. And the other major topic is knowledge representation and reasoning. And this is a very substantial topic. We actually have 2 major components there. One is symbolic approaches, and the second is numeric approaches. This is basically logic, and this is probability. You can think of the first one as representing a reasoning about facts, and this is representing a reasoning under uncertainty. And the other major component is machine learning. So really 4 major components. You can think of this as 1, 2, 3, and 4. And today we're starting with this particular subject. So problem solving using search is a pretty foundational subject. In fact, you can take a whole graduate course just dedicated to the subject. And one of our faculty, Professor Rich Korf, who's an expert on this area and made a number of the seminal contributions in this area, actually does teach a graduate course, which is just dedicated to this. You can think of it as providing infrastructure for other subjects. So you'll see that techniques that we will learn there actually get used in reasoning and also in machine learning. And we will see that later, we'll mention it. And it's a subject that is largely has an algorithmic nature. In fact, in some places, they teach this within an algorithm course. Now, you will have some exposure to what we'll talk about, or at least some of what we will talk about in an algorithmic course, but here it will take a very different slant, and we'll go deeper in this subject. All right, so problem solving a search. And let's go ahead and just give a quick overview of what's going on here, because the picture is pretty interesting in the sense that it's pretty systematic. So this is problem solving using search. So the idea is that you have problems. Let's say we have a problem here, and there is a systematic way for solving a whole set of problems by taking them and then doing what we call a search formulation. That is, formulating the problem as a search problem. Okay, this is the first task. And then there is the notion of a search engine. Okay, this is not like your web search, it's a different story. And then you take your problem formulation as a search problem and you pass it to this search engine, and then you get a solution. Now, there is a number of interesting aspects of this story. One of them is that you would also need to pass to this search engine something that we would call search strategy. Because the way this engine solves the problem to give you a solution depends on what strategy it's using. And there is a number of these search strategies. Actually, let's make this into its own big box here. All right. And we will see that formulating a problem as search is a relatively systematic process. You will have to define, in the simplest form, 3 components or 3 ingredients, 1, 2, and 3, which we'll go over today. And once you have these 3 ingredients, you have formulated the problem as a search problem. And in principle, this search engine is ready to kick in once you give it the search strategy to use. Now, when you look at search strategies, we're going to find that they do belong to 2 different categories. What we will call a blind or uninformed, not a very positive name. And there is the other category, what we call heuristic or informed search strategies. So they do belong to 2 different classes. So what's the difference? The difference is that the blind or uninformed search strategies are good with these 3 components, and they're ready to kick in and do their work. Now, the heuristic versus or / informed search strategy says, you know, I can do better than these guys, but I need more information. So I need a 4th component here, which is known as a heuristic, which in a way tells me more about the problem than these 3 do. And if you give me that heuristic, then I can do my work and I'll do a better job than these guys. Now, what does it mean to do a better job? We will have to do that later, and we will have a very sharp definition of this notion. Now, this notion of a heuristic requires, as I said, further investment in understanding your problem. And there is not just one, there is a whole slew of them. So you can think of them as, you know, these heuristic appearing on a spectrum, and there is a sense of goodness. So the better the heuristic is, and there's a very sharp notion of what better means there, the more effective these guys would be. It can really become a lot of fun when you get into this business. Okay, so what will happen today is we will start by talking about this here, which is how to formulate a problem using how to formulate the problem as a search problem by defining 1, 2, and 3. 4 will come later, a little bit more involved. And what you'd see is effectively, these 3 components are what we call initial state, final state, and actions. So you take your problem and define something that we're going to call the initial state, the final state, and actions. And then you've got a definition of the problem as a search problem. And then the search engine can start doing its work once you give it a search strategy. So we'll mostly look at this and look at a few examples that will help us illustrate this concretely, setting up the stage to start talking about search strategies and the search engine on Thursday. We will start on Thursday with this. In the following lecture, we'll do that. Now, another word before we move on the big picture. It turns out that within this picture, there's a very special class of problems that can be formulated as search. They're so specific in their nature, they're so important in terms of their practical applications, then that they get their own name. And those are known as constraint satisfaction problems, or CSPs. They get their own special treatment. So we'll actually end up dedicating a lecture for those. Again, because they're specific, they allow us to do things more specialized on them, and they're very important practically. Just like I said, you can take a graduate course that's dedicated to problem solving using search. You can actually do, in some places, there's dedicated courses to constraint satisfaction problems, a whole graduate course just dedicated to this subject. And for this problem solving using search, beyond this picture, the last component we're going to do before we move to knowledge representation and reasoning is two-player games. That's connected to the subject. And that basically gives you a roadmap for the next few lectures. All right, so let's get going. And as I said, we will be illustrating these problems that can be formulated as search next. And we will basically be using toy problems, and that will allow us to illustrate things concretely. Otherwise, things will get out of hand, it will be difficult. Someone is asking, is two-player games as in systems that play two-player games like tic-tac-toe? Yes, and more generally chess and so on. All right, folks. So what we will do next is look at two problems that will help us see this notion of how do you formulate a problem using search, or how do you formulate a problem as a search problem by providing these three ingredients. And we're going to start with what's known as the 8 puzzle. You may have seen this. Well, there was a time where everybody would know what this is, and what I'm finding out with the new generations, some of these old-fashioned puzzles are no longer visible to them or of interest. So the 8 puzzle is pretty simple. You have like a board with tiles in it, and in this case, this board is basically looks like this, and you would have, let's say, let's make it like that. Okay, so there are basically 9 cells. And then you have numbers in this board. These tiles have numbers. So this could be 7, 1, 3, 2, 4, and let's say 5, and 6, and let's say 8. All right, so these tiles have numbers and they slide. So you can actually take this tile that has 5 in it and move it to this point, in which case you will have the 5 tile here, and this would become empty. And the idea is I want to move these tiles around so that I will reach a situation that looks like this. Let me draw it here. That's what I'd like to do. I'd like to have 1, 2, 3, 4, 5, 6, 7, 8. All right, so I will give you this board in any state. The tiles could be scrambled in an arbitrary way, and your goal is to go and move them around until you get it to be arranged in this particular way. And of course, in these search problems, we're typically interested in finding an optimal solution. So one of you could solve this by making 10 moves, another can do it by doing 13 moves. We would be interested in the 10 moves more than the 13 moves. Now, if you know about the Rubik cube, that would be another example, more complicated, more difficult, where you have it in some initial state and you want to arrange it so that the colors patterns are in a certain way. All right, so the question is, as simple as this problem is, you would see that it will help us illustrate really the key components that we want, which can be used for something that's way more sophisticated and complicated, like solving reasoning problems and some machine learning problems. So how do you do something like this? How do you solve a problem like this? Now, as I said, I already gave away the three components in the previous slide, which probably should give us a hint. If you remember, I said you need to have three things to define a search problem. The three ingredients, we call these the initial state and the final state and the actions. So in this particular problem, at least a couple of these components are pretty straightforward. So you can think of this as the initial state. All right, so this is the initial state, and we call this the final state. And you can think of this as the final state. So I'm trying to go from this state to that particular state. So here, the notion of a state is just any configuration of the board. And as you can see, in this case, of course, we have a finite number of states. So this is the initial state, and this is the final state. So now what are the actions? The actions, you can think of them as the things that will allow you to transition from one state to another. So in this particular case, one particular action will, we talked about moving the 5 tile. One particular action will move you from this initial state to this particular one. So you would have here 1, 6, 7, 4, 5, 2, 3, 8. Okay, so that was an action. Now, you will need to be specific about the set of actions that you can take. And of course, an action will apply to a state and get you to another state. So let's start with that first. So this is clear. The notion of a state is very clear here. The notion of an initial state is clear. The notion of a final state is clear. And by the way, this is not always the case. So you'll see problems where even what is a state is something that is some kind of an art. Two of you would probably come up with different notions of states. So it's not very sharp. But in this case, it's very sharp what the notion of a state is. So first thing we need to do is enumerate the set of actions before we tell you a little bit more about how the search process works. So the question that I have for you is, let's start with a count. How many actions do I have in this particular case, in this problem? Let's just count them. Or if you want to enumerate them, give me something. What are the number of actions that we have, or what kind of actions do we have in this particular case? Can someone type to the chat box how many actions do you think there is? Or okay, now people are saying 3 actions. I'm not talking about the actions that are applicable to a particular state. So if you look at this guy here, then you can say, move the 6 down, move the 4, or move the 5. I'm talking about in general, regardless of what state we're in, how many possible state. Okay, so people are saying moving a tile is an action. Okay, that's good. So a tile could be moved in how many possible ways? A tile could be moved in how many possible ways? All right, so people are saying moving a tile is an action. Okay, so So people are saying 4 different ways, at most 4 different ways, because I could either move up, down, left, right. Okay, not all of them are applicable, and there is now this notion of whether an action is applicable or not. But yes, a tile could be moved up, down, left, or right. That's very good. And the number of tiles that I have, so I have 8 of them, right? 1, 2, 3, 4, 5, 6, 7, 8. So you may say, well, at most I have 8 times 4 actions. And that's a lot, actually. There's a better way to do this. So people are saying, again, you can move a tile in up to 4 different ways, depending on the direction. And there is 8 tiles that I'm interested in moving. The one numbered, labeled with 1, 2, 3, all the way to 8. But actually, there's a better way to do this. And here we're going through now an exercise of problem formulation. And this is what I mentioned, that it's not always a fixed thing, and different people may do different things. But some formulations are more efficient or better than others, and we're looking at an example of that right now. I'm claiming you can formulate this so that you can talk about at most 4 actions. I don't need to consider more than 4 actions. That's it. Any idea what those 4 actions would be? At most 4 actions. Okay, someone just said it. Said, think about the blank space. Excellent, excellent, excellent. So when you look here, you can say that I moved the 5 to the right, which is what happened. But another way to think about it is that I moved the blank to the left. All right, so this is blank tile to left. All right, and in fact, every action looks like this, right? So this is what happened here. If I were to move the blank upwards, then I would get this particular state. Then I would have 6, 7, and 4, 5. So I'm moving this up, the one goes down, and that's what I have. Okay, all right. So I hope you guys get a sense now of what's going on. Now, you could have formulated this as moving a label tile, and there is that many of them, and each could be, in principle, be moved in 4 possible ways, and you do that, but that would not be the best formulation. This is a better formulation that we're doing now. Fantastic. Okay. Now, let's go to the next step. And in the next step, we're going to just take a little bit of a peek into what would happen in the search engine if you were to give it this problem, right? Because now I'm done. Now I can feed it to the search engine. Of course, we're going to make these notions a little bit sharper in terms of concretely what do you really pass to a search engine. We're getting to that. But conceptually, we understand what's going on. I know what the initial state, I know what the final state, and I have a set of actions. So I'm going to the search engine and saying, engine, get started. Now, the search process that is conducted by the search engine basically amounts to building some kind of what we call a search tree. So let's take a look at this. And this looks pretty simple now, but actually it gets pretty sophisticated and interesting. So if we look at the initial state, and here I'm going to draw it like this, 5, 4, blank. And okay, this is a different initial state than what we had here, but that's fine. So I'm going to say 6, 1, 8, and 7, 3, 2. Let's say this is what you gave me as your initial state, but the final state is always the same, which is this guy. Now, think about this. You can go and say, okay, what can I do in this particular case? How many actions do I have for this particular state? How many actions in this particular situation that I can apply? Remember, we're moving the blank. And in principle, the blank could move up to 4 different ways, but not always. Okay, people are saying 2. So I can go ahead and move the blank either down or I can move it left. Now, if you move it down, look what happens. You get this particular state, all right? And blank here, and then I get 7, 3, 2. Now, if you go ahead and move it to the left, you will get a different state, which is this particular guy. Now, well, let's again hypothetically keep going and say, fine, if I move it down, I go to that state. If I move it left, I go to that state. Well, let's see what happens here. Suppose I'm here. And in this case, how many possible actions do I have? Give me a number, right? We're talking about moving the blank. How many possible ways can I move the blank in this case? Okay, and people are saying 3. Okay, let's do that. Now look what happens here. And now an important concept will come up. So if you move it left, or you can move it down, or you can move it up. And in this case, the state would be 5, 4, 8, 6 blank 1, and then 7, 3, 2. The state here would be 5, 4, 8, and then 6, 1, 2, and then I get 7, 3 blank. Now, if you look at this last state here, what would that be? I'm reversing. This one is reversing. So I moved down and I moved up. So I'm going to get back to that guy up there. So this would be 4, 5, blank, 6, 1, 8, and then 7, 3, 2. Okay. This is what we call a repeated state. This is an important notion that comes out in search. These are problematic in a certain sense, and you can imagine why exactly someone's saying this is actually the initial state. Now, when we playing with this and expanding things a little bit further, we're going to try to actually not do those. But the point is, if you go now to this guy and see how many actions you can take, so you can do this. Now you can grow this further. Okay, I don't know how many states, I'm not counting here. And you can grow this and so on. Okay. And then you're going to get something that's called a search tree. Now, this is conceptual. The search engine is not going to do this literally, because if you do this, you will build a very large tree. Now, I just want to make a few remarks on this, and then I will go to a smaller version of this problem where we can illustrate further points. So here's something interesting. First of all, there is the notion of a path in this search tree. So you can talk about this path here going this way and maybe going that way, all right? So there's the notion of a path where I go from the initial state and I keep going down to some state. Okay, the other thing is, if you do not, if you generate these repeated states, some of these paths will be infinite, right? Because you will keep going. So some of the paths will be infinite in general. And also, some of these paths will contain the final state somewhere, and some will not. Okay, so what I'm interested in is basically a path in this search tree where I will end up having the final state. Those paths are of interest because each one of them represents a solution to the problem, one way of solving the problem, because that path identifies a sequence of actions that will take me from the initial state to the final state. But as we'll see next, the quality of these paths and therefore the corresponding solutions do vary. And this is where things get interesting, and this is where search strategies, as we will discuss them later, you'll see they will do all kind of interesting things. The game of search and the game of search strategies is effectively about finding one of these paths while trying to do two things. One, minimize the cost to find them, and second, trying to find the optimal path. Let's stress this again because you're going to say we're going to spend 2 lectures going over these search strategies. Yes, they're very significant, and what we're talking here is so fundamental, and you'll see how often it comes up. Let me do it here and just give you a sense of what's going on. Yeah, I'm gonna here try to do a simpler version of this. Okay, so give me a second here. I'm gonna start with only 4 tiles. So there is this situation here, and you get to see how subtle this can get. So if you look at this guy and you look at the 2 actions that you can take in this case, it will be either write down, and so I'm going to do this fully actually because I want you to see something visually which will stick if you end up actually seeing it as opposed to just talking about it. So this would be left repeated state, and this would be down. And here I'm going to get 1, 2, and 3 blank. And then here in this particular case, I'm going to have again 2 of them up, that's repeated. And I'm going to have left. And here I'm going to get 3, 1, 2 blank. Okay. Now, that's what we have. And now I'm going to have here, and this is going to be 1, 2 blank 3. Now, here is a goal state. Okay, that is a goal state. So I'm going to go further down, but let's see what happens in this particular case here. So I'm here 3, 1, 2 blank. In principle, here I can do 2 actions, right, repeated state, up. I'm going to get 3 blank to 1, and again down. This is, and then I'm going to do this, and you can see this guy, and then keep going. So this is down, okay, and then this is this guy. Oh, well, so let's continue here. So this was the 2, 3 blank 1, right? So it keeps going. So here. Okay, 2, 3 blank 1. I'm hoping I'm copying it right. Repeated, right? Okay. I hope you get to see what's going on here and what is the point that we would be making. Now let's say 2 blank 1, 3, almost there guys. And here we'll do this guy, and now here we are, and the very final stroke. That's what we have. 1, 2, okay. All right, so that's basically was a continuation here, okay? All right, so I hope I didn't type things incorrectly. There was a lot of typing to do. I hope it was okay, but you get the idea. No, guys, here's the thing. The reason we went through all of this is to make some very important points, which will motivate some of what's going on. Now, this is a final state, and this is a final state. So look what happens, guys, here. What happens is, here's the search tree, and I do have this path here, right? Which is a path I'm interested in because it takes me from the initial state, which is this guy, to a final state. Now, I do have another path, right? So this path here, okay, it's long, this guy here, and I'm going this way, and then I'm getting also to the final state. Now, there's a difference between them. And one of them has a cost of 3, and the other, I think, should have a cost of 9. So they're not equally good, right? So I think this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So one of them can solve the problem using 3 actions, and the other one solves it using 9 actions. And what we would be interested in is basically the more optimal cost, which is this guy. Now, here's the thing. Now, you look at it now and you say, oh yeah, I want to do this. I want to when you started here, whether you took this turn, this action right or this down, big difference. And now when you look at this, you say, oh, of course I should do this action, not the other one. But search engine doesn't see this. And it's not going to go generate the whole tree to do this because it will die. This search tree is exponentially large. And the question is, can it really do the right thing and get you to the optimal cost without having to generate the whole thing? It's a pretty interesting game, and that's what is the game of search or the art of search. And you'd see some very clever things we're going to see later about how to actually do this. I hope you can see how significant this is. Practically will allude to some of the applications later, but if you know how to do this problem well, you can do a lot of things because a lot of what happens can be formulated in these terms. Okay, now let me just make some more remarks on this before we move to another problem where we will discuss some more issues or some considerations that come up with search in the context of another problem, concrete problem. The few points I would like to make. When you're playing this game, there is 2 things you're trying to optimize. I already said them in passing, but I want them to be really imprinted there in your head. One of them is I want to optimize, and this is something that people get confused about. There's 2 notions of cost. The cost of a solution. So in this particular situation, one solution had cost 3 and the other had cost 9. But there is another thing that I would like to optimize. The cost of finding a solution. So perhaps the best way to draw this distinction is I give you 2 algorithms, 2 search strategies, A and B. And both of them are guaranteed always to give you the optimal solution in the sense of cost. Like we'll give you the smallest set of actions that will solve the problem, both of them. Then I will have to ask about, okay, which one of them is more efficient? One of them does that, but it takes a lot more resources than the other. So there's 2 notions of what we would like to optimize. And when we're going to get to this and talk about the various search strategies, we're going to talk about whether they're optimal or not. Typically, when we talk about whether a search strategy is optimal or not, we're talking about this notion. Is it guaranteed to get me the least costly solution? But there is another notion there. Okay, this is something important. The other thing that's important is the cost of an action doesn't have to be 1. In this case, we're assuming that all actions are equally costly. So we're just counting, saying 1, 2, 3, and that. In general, you can have a number attached to each action, and then you want to minimize the sum of these numbers. So in principle, a solution that has 5 actions could be better than another one that has 3 actions, depending on the cost attached to these actions. Now, I want to mention one more thing, and let's see. Maybe we should, let's leave this till later. I have a question for you, but I think you'll be better off thinking about it after the second example. Okay, the final word on this before we go to the next example. What we talked about so far is a specific case of something a little bit more general. I'm just going to mention it. What is this more general thing? So that you know that there is a continuation to the story beyond what we're going to be talking about this class. In these problems, what we talked about the notion of an action is said to be deterministic. That means, let me put this here. This is pretty important. So deterministic action, what does that mean? It means that if you give me a state and you give me the action, then there is another state that results from it. One state, it's clear. Sometimes in certain problems, that's not the situation. So if you apply an action to a state, you may end up going to possibly multiple states. Okay, so this is action. It's possible that you go, so the state is state 1, this could be state 2, or it's possible that you go to state 3. Now, what does that mean? How could that happen? Imagine in robotics, for example, where the action is hold a cup. You know, you want to have the arm go hold the cup. It's and then lift it from the table. That action may succeed or may fail. So as a result of the robot doing this, it may end up holding the cup and lifting it, or it may not. And then the cup will end up staying on the table. So that would be an undeterministic action. The other thing is, what we have here is we know the initial state. Right, so I'm giving you the initial state. I'm saying, here's the state I'm in, and I want to go there. Well, guess what? Sometimes that's also not the case. Sometimes I do not know the initial state. I may know that it's probably one of these guys, but I'm not sure for sure. But I have a final state, and I want to take to find a solution, a set of actions that will get me to the final state, even though I do not know exactly what is the initial state. Again, you say, well, how does this come up in practice? Well, again, let's go to robotics. This happens when you have limited sensing, for example. So a robot, for example, a robot may know that it's on this floor and maybe on this section of the floor and maybe in this room, but it may not know exactly its location in that particular room because it has some limited sensing. And then I wanted to go and end up being somewhere else. And when you have these two elements, non-deterministic actions, we don't know the initial states, that's within the realm of this, but another set of techniques get applied. And then we end up going more into the realm of what people call planning. So planning is a little bit of a more sophisticated version of what we're talking about here, okay? But what we will talk about here is a foundation for solving these more advanced type of problems. We will not get to this, is a little bit beyond what we will cover in this class, but I just wanted to give you a sense of what's going on. Okay, very good, very good. And I'm gonna go get started with the second problem, and we'll finish after the break. But again, one more word on this, just to give you a sense. Even with something like we looked at the 8 puzzle, people tried to do bigger things, like the 15 puzzle and the basically 24 puzzle. This is basically a 5x5 board. And this is a 4x4 board. And just to give you a sense, even though these simple toy problems, if you want to think about them, their search, the state space, that's the number of distinct space, could be very large. This guy here is 1.3 trillion states. All right. And of course, with the techniques that we're going to be discussing later, you can solve these pretty efficiently, even though they have this significantly large search spaces. Of course, this is not the particular interest. These are exemplary problems, but they do bring up the difficulties of these things. Okay, folks, we have another problem of this type, and which we'll do next. And then I want to talk about constraint satisfaction problems, another couple of problems there, to give you a sense of the special class. And that will be mostly what we'll mention today. So let me get started with the, we have 4 minutes, and let me go get started with the next problem, and then we will work on this when we get back. So the next problem that we will do, and let me clean here. Again, it's a toy problem, but it was also one of the first that people started playing with when they started working on these problems a while back. And we can refer to this as the Missionaries and Cannibals problem. Now, you will solve this problem in your upcoming homework. So you probably want to pay attentions. Well, attention, one attention, not attentions. Okay, so what's going on here? What's going on with this guy? So we'll lay it out and maybe you can think about it during the break. So what happens is, in this case, I do have a river. Okay, and so this is the river. And I do have 3 missionaries and 3 cannibals that are sitting on the side of the river. 3 of them, 3 missionaries, and we're going to use the symbol for cannibals, right? So this is missionaries and this is cannibals. Okay, and I have a boat here. And the goal is to move all 6 to the other side. All right. So so you can think of this as the initial state, and the final state is this. I want all of them here, and the boat here as well. However, I do have the following constraints. The boat can take at most 2. This is one constraint. And the second constraint is that cannot have more cannibals than missionaries on any side at any point. All right. So I want to move all 6 to the other side, and I'm going to use the boat for this, but the boat can take at most 2. And moreover, I cannot have more cannibals than missionaries on any side at any point. And the question, how do I actually do this? Okay, this will allow us to bring up a couple of more important issues. And we'll do this when we come back from the break at 11. And as I said, you will be solving this problem during your next homework. All right, guys. So 10-minute break, and we will resume at 11. All right, folks, let's resume our discussion. Now, there was a comment, actually private comment by one of you, and I did miss this. So yes, this is a classical example in many papers, but someone pointed that it does have some colonial and racist undertones. Talking about missionaries and cannibals, they suggested we talk about perhaps wolves and sheep. I will. It's too late now to reverse what I did. I do realize this now. Sorry about this. It's been around for such a long time. We'll try to restrict this to discussions about the X's and the O's. And so basically the boat can take at most 2, cannot have more O than X on any side. I'm glad at least I used O and X and O. So cannot have more O than X on any side. Now, there was some remarks, and I see people are having fun. Someone suggested this problem could be solved by simply having everybody swim. No, that doesn't work. You cannot swim, so you have to take the boat. And the 2 other clarifications on the restrictions is that, yes, we can have all O on one side. That's okay. We just don't want to have the O's outnumber the X's. And the other clarification is no, boat cannot be empty. Boat cannot travel empty. All right. So I hope this clarifies the rules of the game. Okay, guys. So let's get started. Now, remember, defining a problem as a search problem requires 3 ingredients, at least for now. Later, we're going to add a 4th ingredient. So one of them is the initial state. It's very clear in this case. Here it is. And the final state. And then we need the notion of actions. So, and now I need from you to identify the possible actions. This is important. And one thing that we're going to do on this problem, you'll see, is have to do with really how do you communicate actions to a search engine. And that turns out to be a very interesting and elegant story. But let's start. How many actions do we have? How many actions do we have in this particular case? Count them or identify them. How many actions? It shouldn't be that difficult. So someone is saying 6. Okay, someone already went and had and enumerated them and said, well, what we can do is, let's put them here. So if we're talking about the actions, okay, great, guys. So people are some people are counting, some people are enumerating. I think people are getting it right. So basically, we could either move an X alone on the boat, or we could move an O, or we could have 2 X's, or 2 O's, or 1 of each. Okay, these are the combinations. We need at most 2. Of course, as we said, the boat cannot travel empty. So these are the possible actions that we can take, and there is 5 of them. Now, by the way, okay, I did this here implicitly, so we didn't fall into this trap. But if you are starting afresh from this, and someone, when they told you this problem, they gave names to the X's and O's, all right? So let's say abstractly, X1, X2, X3, O1, O2, O3. You may fall into the trap in that case of saying, okay, let's move, X1 is a move, X2 is a move, X3 is a move. And then you talk about moving O1 or O2 or 3. And then when you talk about 2 X's, then you start talking about the combination. Move X1 and X2, X1 and X3, okay. Then you're gonna get a lot more actions, and that doesn't matter. You really wanna abstract the identity of the X's and the O's in this particular case. And that happened automatically because of the way I laid it out, but it just gives you another example of this notion of abstraction and the notion of a state not being sharp. You have different choices for what that is. Okay, I wanna go and just do the first level of the search tree, because I would like to use it to illustrate a number of points. So we're starting here, and we have 3 X's and 3 O's on this side, and that's where the boat is. Now, we talked about 5 possible actions that we can do. And I'm gonna just look at what happens for each one of them in this particular case. So let's say here I did XO, and double X and OO and here X and O. These are the 5 possibilities. And let's see what happens. Now, in this particular case, I'm moving an X and O to the other side. So I'm gonna get this situation, XO, the boat here, and the numbers here drop. So I have 2 X's and 2 O's. So the question that we need to talk about now, and we need to raise awareness, is 2 things. The notion of a legal state and the notion of a legal action. All right, so, okay, I'm gonna put these words here and then we will talk about them just a little bit. Okay, now here I try to move the 2 X's and then that would end up being XX, and then here I have XO, OO, and the boat is on this side. Okay, as you see, this particular state is not legal, right? The O's have outnumbered the X's on one side, and this violates this particular rule here, right? So we're gonna say that this is an illegal state, and basically that's not gonna be here. So we're not gonna generate this particular child. Now, if you go to the one after that, and in this case, I'm moving 2 O's, so I'm gonna get this. Here's the boat. Okay, it's not very clear. I have 2 O's, and this is the boat. And then in this case, I have the 3 X's. And is this okay or not? Is this a legal state or not? This particular one, the one that we just added, is this fine? Okay, someone is saying it is fine, it's legal. Good. So we have 2 more things to consider. Let's look here. Let's look here. So I moved 1 X, and then I have the X, I have the boat here, and then I have 2 X's, and I have 3 O's on the side. And let me do the last one. And in this case, I have 1 O here, and then I have XXX, O. Okay, so I added 2 last guys. This guy, is this guy okay or not? Is this a legal state? Legal state or not? Can I keep this? Okay, and people are saying no. So this is going away, and this is basically fine. All right, so here's what happened. When you talk about an action, so you have the notion of state, let's call it I, and then state, let's call it J, and then I have an action that is taking place that's moving from one state to the other. I need this to be legal, otherwise that action is not applicable. All right. And I also want the action to be legal, because some actions are not applicable to certain states, right? Not every action will be applicable to every state. So now this seems to complicate things a little bit, because you have the notion of states. Some of them are legal, some of them are not. And then when you want to apply an action to a state, it has to be applicable. And not only it has to be applicable, the state that it generates has to be legal. So you may think this will make things a little bit hairy. Now, interestingly enough, and you will see this when you do your next homework, there is actually a nice way to abstract this notion of how do you specify actions, and how do you really hide those details of legal state, legal action, from the search engine, and give the search engine something very simple. So I want to do this next, but I want to bookmark something, and here you guys are going to cooperate with me. I know I put a note here, but I may forget it. So when we finish this next segment about how do you communicate with a search engine, and we'll talk about this a little bit more concretely, please remind me to pose a question to you, which says, what contributes to the difficulty of a search problem? We need to do this before we move to the segment of constraint satisfaction. So one of you heroes out there, if I move to constraint satisfaction before posing that question, do type to the chat box. Okay, now, here's the thing. To make this a little bit concrete, I'm going to show you next how would you represent this problem using Lisp, for example, and what would you have to communicate to a Lisp search engine to solve this particular problem. And you'll see it's pretty actually simple. The key notion is, and let me erase this, and here I'm gonna put down communicating with a search engine. Now, you need to give the search engine the problem definition, right? And the problem definition, as we said, is first you have to give it an initial state. That's pretty simple. And the other thing is you have to give it a final state. That's simple. And we'll see for this particular problem, it's going to be pretty trivial. And then the notion of actions. And as we said, this gets a little bit hairy about legal states and actions. Okay, so what happens is you can abstract all of this into a notion which is called the successor function. What is that? This is a function where you give it a state and it will give you back a bunch of states. All right, state 1, state 2, state n. So it's a mapping. You give it state 2. You give it a state and it gives you back this list. And with the guarantee that all of these states are the result of applying a legal action to the state where the outcome is also legal, right? So each one of these is a legitimate transition. Each one of these is a legitimate transition. This is a legitimate transition from state to state 1. That guarantees you the action that did this is legal and this state is legal. And this is another transition, legitimate transition. That's it. I don't need any details. In fact, in a sense, I really don't need to know your actions. I just need to know that there is an action there that is going to take you from this state to that state. So it's a very simple function, concept that takes a state, gives you back a set of states. And believe it or not, and we're going to see it now concretely, that's all you need to give. You need to give it an initial state, a final state, and a successor function. And then it's ready to do its job. It can help you solve the problem. So let's look at this concretely. So if you look at the problem we just looked at, and let's say how we're going to do this using Lisp. So the first thing you have to decide is how do you specify a state? And any suggestions, guys, here? How do I represent a state in this particular case? You have to think about it. What do I really need to capture? And there's different ways for doing this. I'm going to suggest one, but anybody wants to tell me how we can represent a state in this case? Any suggestions? Okay, someone is saying 2 arrays which hold X's and O's corresponding to which side of the river they're in. Someone is saying 2 numbers. Now, I don't know that we need arrays. Someone is saying 2 numbers. Now, the 2 numbers I'm guessing is what? So the number of X's on the left side and the numbers of O. Okay, very good, very good. So someone says, let's have a convention. I just need to count on one side because from that I can infer the count on the other side. Aha, good. Someone said, I just need two numbers, which is how many X's on the left side, how many O's on the left side as well, and I can infer. And someone added, no, but we also need to know what is the boat position. Excellent. And that's exactly what we're going to do. So we're going to use a list. Okay, how convenient. Being in Lisp, so we're going to have basically a list of 3 elements, and we're going to say that A is the number of X's. Okay, so for what I did here, I did something a little bit different than what's suggested. I'm basically counting the number of X's and O's at the boat location. So this could be either left or right. So the number of X's at boat location, and B here is the number of O at boat location, and C, so these are numbers, and C is basically boat location. And for this, we're going to use, for example, you can do whatever you want. So this is T is boat on right, and then I will have nil boat on left. Okay, so but this list first tells me where's the boat, is it on the left, on the right, and then gives me the number of X's, the number of O's on that side where the boat is, and that should capture the state completely. Okay, folks, we're gonna do two things. Well, let's see, what's the problem? I want someone to basically tell me what the initial state is in this case, and in this notation, what is the final state is, and then I'm going to make a comment about the successor function. So initial state, type in a list of 3 things, a list of 3 creatures. According to this convention, what is the initial state? What is the initial state? Okay, and people are saying the initial state is 3, 3, true, right? And what is the final state in this particular case? Okay, 3, 3, nil. Fantastic. Okay, see how simple it is. Now we get to the successor function. I'm not going to define it, but I want to illustrate it. So what happens here is, beyond having this guy and having this guy, by the way, you typically do not give the final state. You typically give a function that will test whether something is the final state. Sometimes that's what you ask for. It's basically the same. But what I want to illustrate now for you is this notion of a successor function. And in this particular case, the successor function would look like this. So I'm going to give you an example of when you call it, what would you get? So I'm going to go ahead and in Lisp, I'm going to say successor function. I defined one here. I call it successor function. And I gave it 3, 3 to T. Okay. I'm not going to type the answer that I should get here. I want you to help me with that. And while you're thinking about this, I should get back a list, correct? I should get back a list of states. And as you think about this, I'm going to go actually draw a picture on this side so we can end with this story here. Let me see. Very good. So, folks, think about what the successor function should return in this particular case. And I'm going to go draw this picture that visualizes of what's going on. Now, we did this just on the previous slide. We started with this guy. And we actually had, 5 possible things, but eventually 2 of them ended up being not okay. And we ended up having 3 legitimate transitions. Okay, let's say XX, OO, OO. Here's the vote, XXX, da. I hope I got it right. Let's see, 3x's 2, no, there should be 1 O here. 3x's 1 O, and 2x's 2 O's, XO, 3x's, okay, guys. So the question is, that's what happened here. This successor function, which should give me just a list of states, should capture and abstract all of the complications behind this picture. Because remember, in this picture, there was a couple of legal states we had to remove. Now, in this case, these were particular actions that led us, I'm avoiding even mentioning this. And this is the state that we started with, that I passed here. This is 3, 3, true. Okay, guys, anybody wants to type the answer? What should the successor function give in this particular case? Okay, I'm getting a whole bunch of answers. Let me see. Okay, and they do vary. So I think some people flipped the A and B. But one of the answers, at least the very first one I got, seems to be correct, or at least seems to match what I have. Let's do it. Actually, let's do it in blue. So 0, 1, nil, and 1, 1, nil, and 0, 2, nil. These were the states that are returned by the successor function. Let's see. So the claim is that this is 0, 1, nil, and that seems to be right. And the claim here is 1, 1, nil. And the claim is this should be 0, 2, nil. Yeah, that looks correct. All right. So what the successor function did is just took this guy and gave you back that. Okay, I really want you guys to see the importance of this abstraction. First of all, we didn't talk about actions here, right? We talked about transitions. So this is a legitimate transition. This is a legitimate transition. This is a legitimate transition. Now, can you imagine, or can you see why the search engine would be good with this? Because remember, what is the search engine going to do? It's going to start with the initial state and conceptually build a search tree and then find a path from the initial state to the final state. Now, you gave it the initial state. To build the search tree, the only thing it needs is the successor function, because for every node in the search tree, it needs to know what are the children. You gave it that. It can use this guy for that. And then the other thing it needs to know to test whether it has a final state. It's done, it can do its work. And you say, wait, what about the actions? Well, look, what it's gonna give you back is a state transition. It's gonna say, okay, start at 3, 3, and then go to this guy, 1, 1, nil. And actually, let me give you, right. And then it says state, eventually it will end with 3, 3, nil. That's all you need. And that will show you how the problem got solved, because you can infer the action by looking at this state and that state. You can infer the action by looking at this state and that state and so on. So this is all you need to have solved the problem. Okay. I hope you appreciate the abstraction that we did here and how easily you can solve this problem by doing this, and defining this function, and you're done. Anybody want to guess how many actions does it take to solve this problem, by the way? Anybody wants to guess how many actions it takes? Just a rough guess. So people are saying 12. And some people are saying 6, which is about half. Okay, let me say it's closer to 12-ish. Yes, someone said 12-ish. I don't know where you're coming up with this number, but it's actually a very good number. Someone said 11. Okay, hot, cold, we're not going to play this game now. You're going to do this for your homework. You're going to see the actual number, but you guys are going between 10 to 12. That is about right. Okay, now one more subject we need to cover. 9.5. Okay, no, it's an integer, a positive integer. All right, folks. So the last thing I wanted to do is talk about constraint satisfaction, which is a special class of search problems that have their own identity to the point that they will deserve their own lecture. And as I said, there's something you can actually have a full course on. Some people have a course dedicated to constraint satisfaction. Okay, I was testing you guys. You were supposed to remind me to talk about a subject or ask you a question before we move to constraint satisfaction. Nobody did. Ask the question. Thank you, Dylan. Okay, let's ask the question. Let's do this before we talk about constraint satisfaction. The question I want to ask you, and we're going to get to this in more detail later when we talk about search strategies. You guys saw what a search problem looks like. If I were to ask you, and this is based on intuition, I know. When we talk later about search strategies, you get a better appreciation for this question. But I still would like to pose this question. And here I'm going to put it in blue. I'm going to decorate it and glorify it and ask you, what contributes, what do you think contributes to the difficulty of a search problem? You've seen, well, not a lot so far, just a couple. Fine. But I want you to kind of give me some kind of a guess. If someone comes to you and say, hey, we're going to solve this problem using search, and I did formulate it, initial state, final state, actions, and here's this. And you're going to look at it and say, oh, guys, this is going to be really nasty. Or you're going to look at it and say, oh, this is going to be easy. What do you think is going to contribute to that? And I am already getting answers. So people talk about the number of possible states. Number of possible states. Okay, that makes a lot of sense. And we talk about the state space in this case, which is basically the set of states. So the number of possible states, you can imagine the larger that is, the more difficult the problem. And some people are saying, let me see, I see someone said the amount of branches. So if you look at a node, we were talking about, oh, you can do this, you can do this, you can do that. So this is what people are calling the number of branches. Now, you can imagine this will contribute to the size of the tree. Now, this number varies, right? Because it depends on the state, but there is an upper bound, right? There is like, you cannot have more than 5 children or more than 5 branches. So we see in the XO problem, we could have at most 5 branches. In the 8 puzzle, we saw that we can have at most 4 branches. And this is actually called the branching factor, the branching factor. And indeed, it is very important. You may have heard about the games chess and Go. And the one thing you should know is that people spend a lot of time doing chess, and they consider it to be quite difficult because it has a large branching factor, on average something on the order, I think, of like 35. And then for a long time, people couldn't touch Go using these techniques. And the excuse usually here is, why is that? Is because Go has a significantly larger branching factor, which makes these kind of techniques suffer. There is one more thing I want, and in fact, I think it was mentioned by one of you. Let me look at the log here. Now, someone is saying identifying repeated states. This is now a different story. That would be as far as the techniques that the search engine has to do. We're talking about the problem itself. So there is one more thing, and I do believe someone did say, so someone said depth. Yes, Kyle. Depth of the solution. Right? Because think about it, in a sense, all of these three are, in a sense, trying to give you some indication of how large of a search tree you may be looking at. So branching factor contributes. Now, if you have a problem where there are solutions at depth 10 versus I give you another problem where, you know, the best solution has 20 actions, that is a difference, right? In principle, if you were to lay out the whole search tree, then you will find yourself having to go in principle up to depth 10 in one case, but in the other case, you have to go much deeper in order to find a solution. So the depth of the solution, which means how many actions, assuming each action has a cost of 1, how many actions would you need to solve the problem? It's, you know, minimum number of actions to solve the problem. Very good, guys. Excellent. Okay, we're going to talk more about these things later when we get to search strategies, which we're going to start next time. But in the next 15 minutes or so, what we will do is we're going to talk about constraint satisfaction problems. Now, I will give you an example of this, a concrete example, and maybe another one, but just we really need to make two major points. Let's look at this problem, which is usually classically used as a kind of prototypical example to illustrate these. And so we're talking about here constraint satisfaction. Okay, ignore the name, it's a little bit distracting for now. And let's just focus on the problem I'm going to be mentioning. So here's the problem. The problem is I do have, let's say, a chessboard, right? And it's an 8x8. Okay, let me see. Okay, it's too thick. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, okay, that worked. And here's 1, 2, 3, 4, 5, 6. Okay, and not equally spaced. Okay, 8x8 board. And the idea is I'm going to have queens put on the board. And here's 1, and here's 2. Now, I want you to end up laying out 8 queens on the board with a particular condition that I'm going to state now. The condition is that none of the queens can attack another. All right, so this is one particular configuration of the board. All right, so the problem is as follows. You've got a board, 8x8. You've got 8 queens. Go place them on the board so that none of them attacks the other. Now, what does it mean for a queen to attack another? excuse me, a queen will attack another if they're in the same row. So let's put it here. No two queens in same row, in same column, in same diagonal. Okay, let's call these 1, 2, 3. You cannot have this. You're not allowed to have two queens that sit in the same row, in the same column, or in the same diagonal. First question, is this board a solution? Is this particular board that I just showed you here, is this one that we're looking for? Someone said yes, and someone said no. Okay, now I have more people saying no. No, no, no. Okay, give me a violation. Which one is violated, 1, 2, or 3? Okay, people are saying that there is a violation of 3 because actually rule 3 is violated. This queen here and that queen, they're attacking each other. They're in the same diagonal. This is not okay. Okay, now that's what you need to do. You need to solve this particular problem. And what do you guys think? Let's do this. How can we solve this by formulating it as a search problem? I need initial state, final state, and an action. Okay, that's what we're going to end up with today. We're going to come up with one way of doing it, and we're going to make 2 remarks about the special nature of this situation. Okay, someone is already saying that we should have an initial state being an empty board, and then I need the rest of it. And so initial state, and what are the actions? The action could be adding a queen in each spot. And let me read more what people are saying. Initial state is an empty board assortment of an empty board, random assortment of the board. Final state is the right answer. Okay, okay. So, well, let's start with the suggestion that said, let's do the initial state being the empty board. So, initial state. Empty board. Okay, no queens on it. Now, final state. Okay, look guys, what happens in the previous 2 problems. In the previous 2 problems, the 8 puzzle, I showed you a state and I say, that is the guy. Okay, I want to go there. In the XO problem, I showed you a specific state and I said, that is the guy. I want to go there. Now, what is the final state in this case? Can you give me a guy and tell me this is the final state? Okay, now I have to, we're getting to the finish line. I have to look at you guys. Okay. We have to dramatize this a little bit. So someone is saying 8 queens on the board is the final state. No, not any 8 queens on the final, that's not correct. I need those 8 queens to be laid out in a certain way. Okay, and someone wrote, well, actually there are multiple final states. Good observation. We'll start with that. Okay, the final state is a state with no successor. Here's the point. And you already see now what is the issue and why we singled out these problems aside. I don't know what the final state is. In fact, if I knew, I don't have a problem. I solved it. But what I know what to do is, if you give me a state and you say, is this the final guy? Is this the guy you're looking for? I can test for it. So I can write a function that says final state. You give me a state and I can test, is it final or not, by checking these three conditions, 1, 2, 3, correct? So this is different from the previous guy. Now, the other thing is, so there's no notion of a final state. There is a notion of a final state test. That's different. I have a final state test. What are the actions? The actions that people suggested is put a queen on the board. So you start with an empty board and you have 8 queens in your hand and start putting them, right? One after one. And the idea is I only put them so that I get a legal state. So you start with the empty board and you say, put this queen here, put this queen there. Okay, now look what's gonna happen. Look what's gonna happen. In the first level, I'm gonna put the first queen. So here it was empty. This board was empty. And then after I took the first action, how many queens do I have on the board? 1, correct? So now I have 1 queen. And then I go ahead and put the second queen, and then I have 2 queens. And keep going like that. Okay, now I want you to make another observation about this, which is also something that makes this problem special. What's gonna happen here? The search tree, every time I dive 1 level, I add 1 queen. What's gonna happen? Ah, fantastic, guys. Someone said depth is constant, the depth is fixed. 8 moves done. Another way to say this, the search tree is finite, correct? It has a fixed depth, finite, excellent. And I'm looking for a guy at that last level that actually satisfies the constraints that I have. One more observations and we will call it a day. First is the nature of the search tree, or second in our order of exposure. The first thing we said is we don't have a final state, but we have a final state test. And there is one more thing that sets this apart from what we talked about. Remember, what happened in the 8 puzzle? There was the notion of the cost of the solution, which is how many actions. I give you the tiles and you move, and someone can solve it in 5 slides. Another may need 8. I prefer the 5 over the 8. If you're doing the XO problems, there's the number of crossings that I'm trying to minimize. So there is a notion. Okay, I gave you the hint. What's going on here? What is going on here is as far as the cost of a solution. Remember, a solution is a path from the initial to final. Okay, and someone just said all paths have the same cost. So if you're going down, in this particular case, you're going to place 8 queens to get to the right one. The notion of the cost of a solution is not relevant, right? Because really, when you give me the final state, that's it, I'm done. I'm looking for a final state. I don't care what you did internally as far as what actions you took, you got it to me. I have it, I'm done. I'm not really looking for a transition from the initial state to the final state. I'm just looking for one example, concrete state that satisfies my constraint. So even though the setup is exactly the same, what's really happening as far as what I'm trying to get out of your search process is a little bit different. Does that make sense, guys? And you can see why these are special enough to deserve their own thing. They're called constraint satisfaction problems because, and you can see why they're called constraint satisfaction problems, because the problem is defined by the set of constraints. right? You're looking for a state that satisfies some constraints. And that's why they're called constraint satisfaction problems. I'm finding a problem that satisfies these constraints. You can imagine how broadly applicable this is. So people are having a discussion on the chat about the branching factor and all of that. We'll talk about this later. I just wanted to give you exposure to this special class of problems and why we will end up having a dedicated lecture on this. Folks, in your book, there is a section on real-world applications of problem-solving search, and you'll see quite a bit of real problems there. Well, let me ask you, anybody can come up with type an application where you think if you had a software that knows how to do these things we talked about, where can you use it? Okay, I gave you something abstract at the very beginning, that this is underlies some reasoning algorithms and some machine learning algorithms. Okay, but this was just to tell you how tight they are. But forget about machine learning and reasoning. Any idea can you think of a practical problem where you can use this to solve a real problem? Any guesses? Constraint satisfaction. Okay, pathfinding, Sudoku. Okay, all kind of games. Yes. Pathfinding, navigation systems, get me from one place to another. Excellent. Someone saying scheduling. Yes, yes, yes. This is one of the main applications. You know, let's say university, I want to schedule courses, I want to assign times, I want to assign locations for them, and I have all kind of constraints about room capacities. This has to be before that. I may want to generate a schedule for you to graduate, what courses to take in what quarter. And the constraints there are about dependencies. You can't take this before that. You cannot take these courses simultaneously. You have a limit on the number of units you can take. You don't want to mix too many technical courses in the same quarter. You can have all kind of constraints there. I said, give me a schedule. Please propose a study plan for me. It's called a study plan in this case. Beating Gary Kasparov. Yes. You can do that. There's a routing, network routing, you know, in robotics, basically going from one place to another. We mentioned planning more broadly. There is all kind of applications in software and hardware design, pretty right. So there was the story about chess and Kasparov a while back, and of course, a couple of few years back, we had the ghost story as well. So that's a tough time for players. All right, folks, we're done for today. This is all we needed to say. And on Thursday, we're going to start with search strategies. And it's going to be a fun story. So thank you, guys. And I will see you on Thursday.